My name is Paul Tapper and I'm the Technical Director for NUGEN Audio. We make a lot of plugins, including metering plugins. So I've got a particular personal interest in audio metering, and I'm myself actually a mathematician by training. I'm very interested in the mathematics of music and of audio. First of all, why should you use audio metering at all? What's the point of it? A lot of people say audio, it's about what your ears can hear. Why do I care what the pretty pictures are showing me, or why do I care about numbers? And that is true. Of course, the thing which is going to be receiving your music or your audio is going to be the ears and the brain of the listener. But there's a few reasons why you might want to get some extra help, either from some numbers or from the computer or from your eyes. So the first one is listener fatigue. And if you're working on a session, what sounds great at 3 o'clock in the morning after you've had 6 cups of strong coffee might not sound so great the next day at 11 o'clock when you're listening back to it after your first cup of coffee. What you find is that your ears and your brain just get tired of listening to stuff, so you want to boost it up more and more, get it more and more excited. But then when you come back in the morning with a clear head, your perception of it has changed. So through the day, as you become tired listening to the same track or the same piece of audio, you get fatigued. And so the way that your ear responds and your brain responds to that same piece of audio is changing over time. So it's useful to have some objective measure in place, as well as just the subjective measure of your ears. Another important consideration is your ears are hearing the music you're playing out of your monitor speakers, but what if your speakers aren't great? What if you're not familiar with the room that you're listening to? What if you're getting reflections off the walls? What if the stereo imaging isn't quite right between the two speakers? There might be lots of things to do with how your ears are receiving the audio, which means that you're not getting a completely honest or completely full picture of what's going on with that audio. So again, using some kind of objective metering, some objective information, rather than just the subjective information from your ears, can help. And also I've put a line about playout limitations, and what I'm thinking about there is you've got this nice listening environment with these monitor speakers, and you're listening to your audio, your music, and it sounds great. But someone who consumes your audio, if you're producing professionally, someone who consumes your audio might consume it on headphones, they might consume it through a DAB radio, which maybe will be mono. They might consume it through an iPad, where the speakers are really close together. So there's some limitations in how they're consuming the audio, which you may not be fully aware of if you're just relying on your ears with your nice setup with your monitor speakers. There might be phase cancellation problems, which would cause your audio to sound terrible when it was monoed, but you wouldn't be aware of that necessarily just by listening with your ears to your nice listening environment. So commonly, for example, if you're mixing a club mix of a piece of music, in a club PA, it's common practice to mono the bass to help distribute the power. If your bass has got too much stereo in it, there may be phase cancellation, and what sounds great in your stereo listening environment, when it's played out on the club PA, may sound flat or dull or empty or lacking in power. So again, metering can help you to understand what's going on there and help you to avoid mistakes. And then finally on this list of why would you use metering, if you're in a situation where you say you've got a drum loop that you like the sound of, but unfortunately somebody else made it and you can't use it, and you've got your own drum loop, you wish it sounded like that first one, you can use metering to compare your version against the target version and understand how you can mess around with yours, how can you change yours to be more how you want it to sound. And of course your ears are the final arbiter, but you can use extra information. Don't throw away a weapon in this fight of getting the sound that you want by not using your eyes or not using the computer to provide you with extra information apart from just what your ears are getting. So as a little taster, I'm not going to spend a lot of time going through this more kind of traditional set of metering, because there's a specific kind of metering I want to talk about. But as a little taster of some of the information that you could be getting, one of our tools, which is called Visualizer, is a software metering plugin. So if I quickly talk you through what these different views are, on the left-hand side, the top view is showing an FFT view, and that's showing the amount of energy there is in each frequency. So you can find out, well, what frequencies is my audio at? Maybe if there's a piece in the audio that is sounding kind of honky or nasty, you'll see the spike and you'll see where the frequency is, and you can use an EQ to cut that out. And then the lower part of that left-hand side is a correlation by frequency view. So this is an important area when we were talking about mono playout. I was talking about phase cancellation. With that piece of audio, I can see that the higher frequencies are really well correlated, but lower down you can see where the little spikes are coming down the orange. In that area of the frequency spectrum, if I play that out in a mono playout environment, I might lose those frequencies. So if it's down there below that zero line too much, I'm going to lose some of the sound when it gets played out in a mono environment. And then on the right hand side, I'm showing a few different views. There's on the top there's a stereo spread by frequency view, so you can see where the frequencies are panned left and right in different frequency bands. Below that there's what's called a spectrogram or a waterfall view. So you're seeing the different frequency energies moving up over time. And it's a different way of looking at the same data that you've got in the FFT view on the left, but displayed in a different way, and it can help your eyes to see different details. Again, to inform your ears. It can become quite an intuitive process rather than having to analyse what the pictures mean. As you use an analyzer or a metering tool, your eyes become accustomed to connecting that with the sound that you're getting, and it becomes more intuitive and more natural. Then below that there's another one, which is the stereo panning spectrogram. So it's a bit like the view at the top, which is showing the panning by frequency, but again this is a waterfall view, so it's moving over time, and again it gives you information of how over time different frequencies are panned left and right. And then at the bottom there's an overall correlation meter. So again, correlation like the correlation by frequency view, this is showing an overall correlation of the audio. So it gives you an idea of overall, if your audio gets played out in mono, how much of it's just going to disappear or how much is going to be left intact. So those are all pretty traditional kinds of metering that you would want to use to inform your mixing decisions when you're working with audio. But I want to talk particularly about these two areas, loudness and true peak. Now these are areas which are new to the music industry. They're something which have been introduced in broadcast audio over the last few years, but it's a new area for the music industry. The idea of the loudness war in the music industry is a well-known concept. Since the 1950s, 1960s, popular music has got mastered louder and louder and hotter, so that now if you compare a popular top 10 track now compared to what it would have sounded like in the 1950s, the current day music is a lot louder and doesn't really sit well next to audio which is from the 1950s or 1960s. And that's because there's a perceived competitive advantage in mastering your audio louder and louder and louder, because it will stand out compared to the other tracks around it when it's played out on radio. And because if you listen to the same piece of audio and then you listen to the same piece of audio 2 dBs higher, say, the second one will just sound better. Our ears and our brain just likes loud things in the short term, but in the long term it can become fatiguing. So in popular music there's a competitive advantage, or there has been up until now, a competitive advantage in getting louder and louder and louder. So people make more and more use of limiters and compressors to reduce the dynamic range and get hotter and hotter music. Now this has also been true in broadcast, in commercials. If my commercial selling a dishwasher is louder than the next commercial selling a car, my one's going to stand out better. It's going to get more attention. And so broadcast audio guys making commercials had this competitive push to turn the volume up, turn the loudness up more and more, compress the audio more and more. So that's what happened. But then complaints to broadcasters about the loudness levels of the adverts, the commercials, became too much to ignore. And a few years back, legislation came in the US with the CARM Act, and throughout Europe and in Japan and in many other territories, there's agreements between broadcasters to measure not just the peak digital level of audio for broadcast, but the actual loudness level. So nowadays, on TV, adverts are measured for loudness, not just the peak level of the audio, but the overall, the average loudness level. And they're what's called loudness normalized. So now, if you master a commercial for broadcast louder than somebody else's commercial, you don't get any competitive advantage. It'll just get turned down because they're all getting loudness normalized. So that's a change in the competitive environment for an audio engineer working in commercials for TV. So that revolution which has happened in broadcast is now beginning to come into the music industry. And last year at the AES in New York, Bob Katz, a well-known mastering engineer, announced the end of the loudness war for the music industry, saying that there was no longer any competitive advantage for having one music track louder than another one. Well, that's maybe not completely come about yet, but it is a process which is going on. And more in music now, there's less point or less advantage in being louder, and there's possibly some disadvantages, which I'll talk about in a bit. So in the music industry, again, if you're a professional mix or mastering engineer, you're thinking about where your audio is going to get consumed. How is it going to get played out to the listener? And they maybe will get it on a CD, but nowadays it's probably more likely that they're going to get it from some music streaming service, maybe from iTunes Radio or from Spotify or Pandora, or maybe they're going to listen to it on a digital radio. All of those different contexts are beginning to use loudness normalization. So for example, on iTunes Radio, if you listen to a track from the 1950s and then you listen to a track from the 1990s, they will sit together properly because they're getting loudness normalized. So if you're a mastering engineer and your main effort is to make the audio loud, that's not going to give you a competitive advantage going forward because the computer is going to turn the music down to loudness normalizer. So as an example of this, on the left, ZZ Top's Sharp Dressed Man, 2004 remaster, and then on the right hand side, Peggy Lee's Jump for Joy, and that's a 2014 remaster. Now just looking at the waveform, you can see that there is a really big difference between how the two pieces of audio have been approached. ZZ Top has been compressed within an inch of its life, and you can see it's flatlining the wave, whereas Peggy Lee has been given a lot more dynamics to play with. There's a lot more room in the mix. There's been less use of compressor and limiter. So not surprisingly, ZZ Top is a lot louder than Peggy Lee. And the graph below the waveform is showing the loudness levels. The red line is the short-term loudness of the audio. And the loudness is measured using an algorithm which is used throughout broadcast. It's agreed international standard, an ITU standard. So looking at the red line, ZZ Top is constantly very, very loud all the way through, and Peggy Lee kind of jumps around a bit. So if you listen to the two tracks without any loudness normalization, ZZ Top blows you out of your seat, and then when Peggy Lee comes on, you've got to turn the volume up because she's too quiet compared to ZZ Top. But what about if we listen to them on iTunes Radio or Spotify? Now, in the bottom picture, I've loudness normalized the two tracks. So the average loudness, which is what's used to balance the loudness of the audio, is the same for ZZ Top and Peggy Lee. And this is how it would be consumed through a music streaming service, through Spotify, Pandora, iTunes Radio. So the computers turned ZZ Top down because it was just too loud. It wasn't going to work next to Peggy Lee. And now on the left-hand side, ZZ Top is still pretty much a flat line in terms of loudness, but they've been averaged out against Peggy Lee's average. Now if you listen to the two tracks next to each other, they do sit well together. You don't have to turn the volume up when Peggy Lee comes on, but there is still a difference between the two tracks. ZZ Top sounds pretty much the same level all the way through. Doesn't get any quieter, but it doesn't really get any louder either. Whereas Peggy Lee, she's got little quiet bits and then louder bits. So the green lines I've drawn are the maximum loudness that the two tracks reach after they've been loudness normalized. So this is real world. This is how these two tracks would come out in iTunes Radio. Peggy Lee would actually have louder bits than ZZ Top ever got. The loudest bit of the Peggy Lee track when it's played out through a music streaming service is louder than the loudest bit of the ZZ Top track. So that's kind of inverted in your thinking. Because ZZ Top was mastered so loud, it ends up that when they're loudest normalized, that Peggy Lee has areas which are louder than the loudest bits in ZZ Top. In some senses, you could say that Peggy Lee was louder, although on average it's exactly the same. Another problem that this overcompression causes is that effectively ZZ Top has thrown away some of the headroom. When it was mastered, it was pushed up into the limiter and the compressor, and the signal was pushed up to 0 dBFS. It's making full use of the digital headroom. But then remember, when it's loudness normalized, the computer turns it down. So now all that headroom has been pushed down. And in the bottom graph here, the blue line is showing the digital level, the signal level. So a ZZ Top, again, is pretty much a flat line. It was pushing right up into the 0 dBFS when it was mastered full range, but now it's been turned down. It's dropped down by 10, 15 dB below 0. All that headroom's got thrown away. Whereas Peggy Lee, because she's not getting turned down, she's already the right loudness level, there's loads more use of the headroom. And so the transients are a lot more alive in the Peggy Lee track than they are in ZZ Top. ZZ Top's got a kind of almost like a woolly feel about the transients. There's less attack, whereas Peggy Lee's still got all that life in the mix because it wasn't overcompressed. So because this is a new concept really in the music industry, a new problem that music mastering engineers have got to try and solve, to help music engineers understand that change and understand how their music's going to sound in a music playout service, we've just introduced this new tool called MasterCheck, which allows you to listen to your music when it's been turned down to the correct loudness normalization level, so you can see what your sound is going to sound like when it is played out compared to other tracks. And you can also measure the PLR, which is the peak to loudness ratio. And this is a measure of how much the headroom are you using, how much headroom are you going to lose if your audio gets turned down when it's loudness normalized. So I also want to talk about true peak level. So we're all familiar with the idea of digital samples, digital audio, and digital peak level. The smooth line is what the original analog audio signal was like, what the compression in the airwaves was like. And then the dots are the digital audio samples. So if I'm measuring what the peak level of that audio is, if I just measure how far away do any of those digital samples get from 0, I get the green lines here. They're fine, they're below 0 dBFS. That's perfectly legal, great. But the problem is that the underlying analog signal, which was represented by those samples, isn't okay. It goes over the 0 dBFS. So I've marked in that with the red lines. You can see below and above, that underlying signal has gone beyond the clip level. Well, why is that a problem if the digital samples are okay? Why do I care? Well, if your audio is ever going to have a codec conversion, then you should care about it. Now, it may be that you're going to master it in PCM WAV form, and everybody who ever listens to it is going to listen to it as a PCM WAV, in which case, well, maybe it's not a problem. But if it's going to get converted to AAC or MP3, and certainly if it's ever going to get streamed out through a music streaming service, then that's definitely going to happen. It's not going to get streamed uncompressed. Then there's going to be a codec conversion, and that's making use of that analog waveform between the digital samples. So if you've got a level which is beyond 0 dBFS in the underlying analog wave, you will probably get clipping or fizzing or a sort of a busyness in the sound, which isn't necessarily a problem for the first track, but becomes fatiguing on the listener. And so to try and get around this problem, part of the loudness standards is to measure what's called the true peak level. So this is, if I just go back to that previous one, the true peak level is a measure of how far does the analog signal get, not just what is the maximum level of each of the digital samples, but what's the maximum level of the underlying analog signal. So that's called the true peak level, and it's true in the sense that it's a measure of the underlying signal, not just the digital samples. So there's a few things that you need to be aware of with true peak. Certainly if you're producing broadcast audio, then the true peak level will be measured now, not just the peak level. And if you get a true peak clip, then that audio will be rejected because it will cause problems further on down the playout chain. If you're using a traditional limiter, then the chances are, as you push your audio into the limiter, that will cause more and more true peak overs. It tends to push the audio out of the legal limits. So it's important that you meter the true peak level, not just the peak level. And again, in this situation where you're just relying on your ears and your monitoring environment, you're not going to hear straight off where there's a true peak clip necessarily. But if your audio then gets converted later on to AAC or MP3 or some other compression format, then it is going to become a problem which you weren't aware of just using your ears. Again, you need to use these tools to provide you with information that your ears won't necessarily get just on their own. Or you could even use a limiter which is designed to limit the true peak level, not just the digital peak level. So in conclusion, that's the end of the talk, metering is a way that your eyes and your brain, the numbers and the computer can help your ears. You're not just reliant on the subjective, but there's a bit of science can help inform what you're doing as well. It can give you important information about how your music's going to get played out, which you won't necessarily be aware of just from listening to it. And thirdly, the area that I really want to highlight is it can help you to adapt to this new, changing competitive environment for the music industry. As audio gets loudness normalized, it's a change of what's going to work, what's going to sound good, what you should be aiming for. If you've got any questions about the talk, feel free to email me. Thank you.
That was an awesome presentation. I had two quick questions for you.
Yeah.
What's your take on, you said with the loudness war, like digital streaming, they're bringing it back down. What's your take on like YouTube? Because I know like for YouTube, their like standard is kind of like -3 dB FPS. So what's your take on that?
Personally, I think that the loudness revolution will eventually reach all parts of audio, because the end result is that it improves things. And you can get a bit of a rocky ride on the way there, but in the end, audio that's been loudness normalized, because it removes this competitive pressure to over compress things, it ends up with more freedom for the audio engineer. So audio that's played out in a loudness normalized environment ends up just being better. So I think that obviously the internet is very unregulated, but over time, I imagine YouTube at some point will say, we can introduce loudness normalization. It'd be a pretty easy thing for YouTube to do. And then that revolution would spread into the internet, because if you're making an internet video, you're going to put it on YouTube. So I think it'll work its way through the whole system, all audio.
All of the internet-based platforms are pretty much on the same level then, like SoundCloud. YouTube.
I think they will do. They don't yet, but I think they will do eventually. Yeah.
Your plugin for the True Peak.
Mm-hmm.
How does that kind of differ from an Avid in Pro Tools already? You can actually see like the peak when you click on the metering. How does that? Is it just more accurate for your plugin?
So the level meter in Pro Tools is digital peak level, and that's fine for most purposes. If you've got a whole bunch of tracks, then just measuring the digital peak level is going to be fine. But for your master track, because the mixdown might end up going through these codec conversions, you need to be aware of not just the digital peak level, but what's happening in between the digital samples. So that's where you need to bring in this true peak metering. So personally, I would just use the Pro Tools levels for all the tracks, but then on the master track, I'd make sure I had some true peak measurement, and maybe a true peak limiter.
Wouldn't you want to monitor that in the analog layer as well, though, prior to getting into the DAW itself?
Yeah, I guess so. In the analog layer, then that's got the whole waveform there. It's really when you go into the digital domain that it's a problem, because you can be lulled into this false sense of security because of the digital samples.
Awesome, thank you.
Great, okay, thank you.